So our next panel, my good friend Brian Bailey from Semiconductor Engineering will lead this host of verification experts in discussing those darn bugs. When will they be exterminated for good? Take it away, Brian.
Thank you. So, is it possible for any system to be bug-free? I'd like to start with a little story from 43 years ago when I was an intern working in an avionics company in England. We were designing one of the first commercial fly-by-wire systems, and I was an intern. I got all of the grungy jobs, and at one point, one of our prototypes, because we didn't have simulators back then, simulators were just a dream, we created prototypes. And it's actually good that we did create a prototype, because a simulator would have never found this problem. But the problem was that one of these prototypes would occasionally lock up. And my boss said, why don't you find out why that system locks up? Well, it took me a couple of days, and then I found out the reason was because it had a weak power supply. And every so often, the voltage would drop, IR drop problems, and the system locked up. Easy, put in a new power supply. Well, that isn't really the bug. It was a symptom, so I was told to go back and continue looking for the real problem. So it took me another few days before I worked out that what was happening was when the voltage drooped on the power supply, random data was getting latched onto the bus, and this was the beginning of a pretty famous series of events with the Motorola 9D opcode. The 9D opcode was a test mode for the 6800 processor. And what it would do is it would cycle through all addresses in memory. The instruction never ended. And because the instruction never ended, it never responded to an interrupt of any kind again. Well, this is a big problem for avionic systems that rely, and for many embedded systems, that rely on a periodic interrupt to start off a new cycle of computation. Well, this was why the system was locking up. Now, was that a bug? Motorola didn't think it was a bug. They specifically designed it in to help them test the processor. Within the English avionics and military system, it was a catastrophic failure. This bug actually caused, in effect, a recall of every application of the Motorola 6800 in any aerospace and military and defense applications. They all had to be retrofitted. Now, in that case, the retrofit was, well, you can't use the interrupt, you use the reset instead. Something that the specification specifically said you can never use reset while in operation. That was the only way to fix this problem. Now, I can't even begin to imagine the number of bugs that fixing that one bug was now going to create with all of these systems that never expected to get used in that manner. And so that to me is a demonstration of why we can never even contemplate a system that's bug-free. At best, we hope that we can move the bugs to a place that we don't care about. And that to me is the best case scenario. So we're going to discuss this today. We're going to discuss if it's possible for any of these systems to be actually bug-free. And joining me today, we have Ashish Tabari, an expert in formal verification and CEO, founder of Axiom-Eyes. What am I talking about? Not Ty. I'm sorry. No, Ashish. I will start this again. Ashish, yes. So the founder and CEO of Axiom-Eyes and a very renowned expert in formal verification. Ty Garibay, processor development expert, and you've now got to be involved with analog now as well as digital, and we tend to leave out analog a lot when we talk about verification. Mark Glasser, I've known for so many years, and I think probably one of the foremost person with a lot of the standards for verification that we use today, that's been the driver and pushing a lot of these things forward. And Larry Lapidus with Imperus, who has probably seen more verification technologies get into commercial adoption through various companies than a lot of other people. So before we really get going, I want to remind you, this is your panel. It's not my panel. If you want to listen to my boring questions for the next 45 minutes, then that's your problem. I would love to hear your questions and to drive this panel in the directions that you want to go. So I will just start, gentlemen, is it possible for any system to be bug-free? Why don't you start, Larry?
Thank you. Thanks, Brian. Thanks for the introduction. Thanks for just putting me on the spot. But actually, I'll say, do we care if it's completely bug-free? Because will we know that it's completely bug-free? I'm not sure that there's necessarily a way to know if it's bug-free or not. And so we're just going to keep on working on verification, because with verification, your job is never done.
Mark, do you care if anything's bug-free?
Well, I agree. There's no such thing as bug-free. So people make mistakes all the time, all day, every day. The best evidence of that is the fact that every single keyboard that's ever been manufactured has a delete key on it. Right, so I mean, it's probably the most used key on the keyboard because people make mistakes, right? And so the best we can do is try and mitigate that and find the mistakes and correct them. But I don't think we'll ever stop making them.
Ashish.
Yes, I think we can make systems bug-free. So I'm a formal verification guy. People come to us because they are struggling to find those last corner case bugs. The randomization is not catching up. Directed tests are only so few or so many you could run. I think the bigger question is, if we are determined in knowing whether we're building the right product. I think in the story that you narrated, it seems to me that part of the problem was architecture itself and knowing what the requirements were. I think we are asking this question in 2022 because we're not doing very well with the verification health, and therefore we are actually forcing ourselves to ask, are we actually going to be able to build bug-free? I think if people used more of formal methods, then I would argue we could eventually build chips which would not need updates after updates. That's my view.
Before I rip into you on that, I'll give Ty a chance.
All right, I guess I'm just in the way until Brian can take care of Ashish. So, yeah, I guess I tend to agree with the first two answers more, in that I believe that to some level we can get bug-free-ish, but being human beings, we will simply then do something more complex and stupid. So therefore, we will create new bugs at a higher level, at greater integrated complexity. So, the theme that I'll probably come back to on a regular basis is, where we're headed in multi-chip packaging and chiplets, where we can go back to the beautiful days that you talked about of we find problems only when we integrate what we thought was a standalone product with other devices that were conceived as standalone products. And now these are being designed by two completely different teams. And of course, they will encounter use cases that the original designers never anticipated, which is basically the definition of a bug case. So, I think as we raise our levels of extraction, as we continue to build more and more complex systems, bugs are unavoidable, and really it's more how do we deal with them. Go ahead, Brian.
Go ahead, Mark.
So I want to address that issue. So the when we talk about in verification world, we talk about making sure that the design matches the specification, and so that's the kind of the golden reference, right? We have some model of the specification, and we see if our RTL, our implementation matches that. I would argue, though, that we don't know if the specification is correct. And that's where I think the problem is. I think this shows up in the formal world, too, right? So you never know if you have the right set of properties, right? You never know if you have enough properties.
Yeah, exactly right. And I'm glad you brought that up, because when I look at the bug-free, I'm looking at the verification problem, whether the design implementation meets the specification. We are not necessarily saying whether we're building the right product itself, which is the validation question, which is what Mark is alluding. And yes, there are a hell lot of questions that we need to answer for the full system integration, software stack, the use mode. I'll tell you a little story, really short. I used to work for a motor manufacturing company in India when I started my career, Crompton Greaves. All of these motors were used in washing machines, and they were being sold in mass. And one particular day, we got a whole batch coming back, and nobody could figure out why these motors were getting broken and why these washing machines were not able to sustain. Turned out that some people in India were using those washing machines to wash utensils. It's a validation problem, right? The vendor had to fix it, of course.
It seems as though in some respects we've always built systems to be somewhat bug resilient, in the fact that if we accept there will be bugs, then we just try and make sure that when they are found, that they don't cause a catastrophic failure of the product, that they can be somewhat degraded and a software workaround or something like that. So do we even need to bother to try and be bug free? Can we just be bug resilient?
Oh, that's a tough one. I'm not sure I agree with the premise that we've designed these systems to be bug resilient. I'd say it's just in the general nature of the designs, and in particular the processors that give us this flexibility. So I'm not sure that's designing in resilience to begin with, because the power of the processors is actually something that's needed here. And as we've been talking about this verification and validation question, and so flipping back to something else, with testing the design, implementation, the specification, the reference model, there's also the test bench itself to be considered here. And when you have a failure, doing your triage, figuring out where that failure is a significant task. And maybe the weakness in verification right now might be better tools for figuring out where the disagreement is, as opposed to anything else.
So I think you asked, is it good enough, or is the real goal to be bug resilient? This works by definition for systems that have software, that have a processor that can execute software. You mentioned that our current company is doing analog. It's a fundamentally analog compute. There isn't a lot of software involved. At a higher level, there is, of course. But a bug in the full custom layers is a bad thing. And so I think in many ways, yes, we can. Our best case is that our systems are designed to be bug resilient, and the bug shows itself at a level where some form of software intervention can affect the bug's behavior in some way. But the reality is, there's always going to be layers of the design at the lowest levels that just doesn't apply.
So, if you look at the data, and I know Harry is sitting here in the audience, and in his Wilson Research report, he mentioned that a high number of, about 68% of the ASICs are going through respins. That is not bug resilience. That is people actually redoing the whole thing again, and that is very expensive. And for us to sit here in this day and age and say this would be acceptable moving forward is not right. Something has got to change. We need to take a fresh step, take a look back. And I'm not talking about solving complex problems like you cited, which is on the threshold of validation, or what Ty might be looking at in the analog. I mean, even if you just look at the whole digital framework, the amount of hours, processor companies are hiring 5 times more verification engineers than designers. Imagine trying to then be part of the 68% of these people who can't tape out on time or have to respin. So, yes, I might sound like a perfectionist. I'm a formal guy, likes everything proof, but no, I realize bugs, we can't root out everything, okay? We can try and work as hard to do that, but we are way off from even coming close to saying, I routinely work with teams in different customer accounts, and with the heavy simulation investment and emulation investment, in some cases formal, the fundamental approach in verification, which is to leave a lot of the corner cases in the hand of random seeds, is not going to scale. And we need to accept this truth and really need to ask ourselves, should we change something? I'm not afraid sitting here now in San Francisco saying this. I'm not saying that formal would solve everything. We need all of the key technologies to come together, but we need to ask the right question at the right time and use the right technology for the right reason. Yeah. And yes, I think it will be asymptotic. We will not build a completely bug-free chip, but we will come very close to then be able to ignore any of the minor defects that may still leak.
But fundamentally, for the last 20 plus years, we've been banging our head against the wall with exactly the same tool suite. We haven't advanced anything, have we really? It's sort of, if we can't solve the problem, why aren't we fundamentally looking at changing how we tackle the problem?
So let's look at what the nature of the problem is. So I did the math for a talk I was doing on functional coverage. For a simple device with 100 pins and 8 32-bit registers, the total number of states that thing could be in is 10 to the 88. And if you did one state per microsecond, it would take you, I don't know, some thousands or millions of years to get through all of that. So and that's not even a real world device anymore. That's a very modest, simple device. So for a real world device, the size is even more astronomical than that. So that the idea that we could touch every single state and claim absolutely that we know that everything is correct is virtually impossible. So the best we can do, no matter what, is to try and figure out what, which swath of the state space is important and which is not. And I contend even in the formal world that's still true as well, because you have the same problem. That the state space that size, there aren't any computers that can manage that.
So yes and no. So the numbers that you're saying are, in all humility, I would say that we can walk through a state space as big as that within minutes. I can tell you we are looking at designs with 10 to the power 300,000 states, and we're finding bugs with formal tools. I can tell you that we recently looked at a block where we had 10 to the power 38 combinations that could manifest. Formal tools are verifying this in 90 seconds of runtime. I think, yes, we can't verify exhaustively everything. I totally agree. It's a risk management exercise. Yeah. We should look at the things that we care most about. But I think if we take a step back and ask the same questions, okay, it is a hard problem. We didn't do very well last time with X, Y, or Z. Can we try something different, look at it from the fresh perspective? Often the answers are just next to the, it's not as bad as people think. Yes, the tools and technologies have come up, but I think it's all about how you approach the problem-solving side of it. I can tell you that the same designs I'm talking about are virtually unverifiable with formal if you ask the question in a different way. So it is not that different from UVM. UVM is methodology, right? At the end of the day, you've got so many organizations around the world, including EDA and adopters of UVM, who are still developing cool ideas, tips and tricks. It's a far more mature technology and far more users. So people kind of know, and formal, for whatever reasons, hasn't had the adoption that UVM had. But wait a few more years, and you will see that there will be far more people with a deeper understanding of these tips and tricks and methodologies and whatnot. So I think it's a positive outlook from my point of view, Mark. And I do want to say, I'm not saying we'll verify exhaustively every chip, but today I can tell you we are verifying 64-bit out-of-order RISC-V cores exhaustively with formal. I mean, 4 o'clock I have a talk at the Cadence Theater, and I'll tell you all about it as to how we're doing it, right? It can be done. I'm not saying I'm going to verify your next network on chip exhaustively in 1 hour, but it's how much time, again, what level of people are doing the work, etc. Those challenges are not very different from UVM or even emulation, right? The level of skill that is required to drive an emulator and debug.
Well, it's about coverage, right? It's about getting as much coverage as you can, covering as much of the state space as you can in the shortest amount of time.
That's right. So we have the tools and the technology.
One of the things you said, I hark back to that, and you said it could have been impossible if the question was asked in a different way. Right. This is why I've always said that when you buy a formal verification tool, you also have to buy the 2 or 3 PhDs that actually know how to use it. So that's you're right. It is a methodology issue that we're still figuring out how to use these tools the best. But to Brian's question, the initial statement, we haven't made any progress in 20 years is obviously false. We are building regularly, tens of billions of devices, of transistors, devices that mostly work, and that's almost verging on the level of magic. In my case, we have a analog device that has 20,000 A to Ds on each chip, and it mostly works. I contend that this is indeed black magic. So we have made a tremendous amount of progress. It's just that we happen to be in a business that tends to, grow the horizon every 18 months to 2 years, right? So the challenge gets better and more interesting, which is why we keep doing it, which makes it fun.
Harry, you have a question.
To the question, I don't think anybody answered Brian's question. But, and I don't think mostly work is good enough, because if you look at the mass costs at 3 nanometers compared to 24 nanometers, it's 25x more. If you look at the wafer costs, it's 10x more. So even if you're just treading water, you're doing worse. And the question is, can we afford this in the future?
So, good question, Harry. Thank you. I'd actually like to, in responding to that, go back to Brian's question about resilience, and wonder here a couple of things. One, are we getting better as we increase in complexity? Is the increased use of design IP actually going to be a help in reducing the number of bugs? And second, the same thing from a verification IP perspective. Does that help? And in particular on the design IP side, we've got a couple of folks up here, in Mark and Ty, that are working on AI sort of designs, and there's a lot of design IP used in those, and potentially a lot of flexibility there and resilience built in. And so with some of these chips, maybe most of the chips that are going to be built at these advanced nodes, are they going to have more resilience built in just by the very nature of the design? And that's both, maybe it's not building the resilience in deliberately, but it's just the nature of the target application there.
I think bug resilience might work for mobile phones, for non-critical chip infrastructure, but if you're supplying to safety-critical domains, we can't tolerate the failure. Famous company made an error many, many years ago in a floating point calculation. Everybody knows what happened after that. If you are into mass production of high-end servers and chips, that is going to affect people's lives. it's only a matter of time when you get sued. Whether you call that a feature, you call it whatever you like, but it is coming down our way if we don't change and we don't do it in a step way. So I think bug resilience, yes, we would need more software updates, activate chicken bits, whatever you want to call it, right? But that can't be the starting premise of verification. Let's go verify this next generation chip. Most of it was working because it was deployed in the field for 20 years, so it's silicon proven, right? It might have been silicon proven because it was deployed in a domain where it met the requirements of the domain. Now it may not. So it's really full circle coming back to what you were saying, right?
We do have another question.
Yeah, so I happen to be from that company that had that floating point error.
Which company? I didn't.
Intel. In any case, but okay, so my question is actually for you, and that is in the formal space. I don't see a complete solution yet. You can't just create like an arbitrary set of properties and just expect a formal tool to go off and prove it. So where do you see the frontiers right now, and how do you see the field progressing over the next few years? What kind of technologies are going to be important?
It's a great question. So in terms of tool technology in the hands of the EDA, they're actually doing a significant job exploiting machine learning in the back end. But in terms of using, and going back to what you said, how do you come up with some random set of properties, a systematic set of properties? It's all coming down from a specification
Well,
document.
it's not just coming up with the properties, it's verifying them.
Yes, that's right. So knowing what you're going to write is the first challenge.
Yeah.
It comes from specifications, which may or may not be in the shape you want. Coding with a skill to guarantee proof conversions is where the methodology question comes in. This is where we come in. We like to solve that problem. And determining whether the methodologies we used were able to sign off with quality is the coverage question. And we know what we can do with the formal coverage, regardless of any tool vendor. I'm not actually batting for anyone here. We can do things with all tool vendors in a completely tool-neutral way to answer the basic questions around functional coverage type challenges that are known to us in simulation. I call the scenario coverage. We have code coverage. We have checker coverage. We have mutation coverage. A lot of the technology is advanced and mature. The problem is what you're hinting at is the consistency is not there. The rule books are not there that could be deployed across the industry. That I accept it's a gap, and companies such as Aximize should do more to
Well, there's
minimize
another
that
problem
gap.
area as well, and that is with global level properties. You get massive state explosions, and all the tools that exist just sort of blow up. And is there work in that area?
Yes, there is, and in fact. That company I was referring to that made the Blender has made a lot of investment in advancing formal, and they regularly publish papers where they talk about those methodologies. And there are other companies too, including ours. We talk about it. I mean, it's not that different from how you're building a design. If you were building a new design and you had a new designer and said, what are those things a designer can do to make this design work out of the box correctly with all the features? What is the rule book? Tell me the name of the rule book that every designer can use in the world to become a good designer. Does that book exist? I don't think so.
Yeah, that's another interesting question.
So something that has come up a few times is, you're talking about priorities. What properties do you develop, or what areas with random do you go after first? How do you prioritize? Why aren't we kind of trying to formalize that description of where our priorities are? Isn't that the first part of trying to put together a formalized specification that we're trying to meet?
Yeah, you are right. And those organizations who have very advanced use models for formal simulation and emulation actually do that very well. There are not that many, but the big ones do have teams of people where simulation, formal, and emulation teams would sit together and routinely partition the verification concerns. But it's just there are a handful of these companies, right? I don't know that there are very many, but that is exactly what needs to be done. Formalizing is actually going to the next level, and I'm thinking now from a formal way of formalizing, but even writing down the plan in a 4-page document which describes how these technologies would be mixed would be a decent start. But accepting that we even need to do this is the first one.
So, Mark, how do you find within teams, how do they go about this prioritization process? Or is that just where the experts come along and say, this is where we should be spending the time and effort?
Well, it's a number of different things. So that's one of them, right? So you want to write down all the different behaviors that you want to make sure work correctly. We call that a coverage model, right? So you need to develop a comprehensive coverage model. But you also need to look at workloads, right? So what exactly are you going to be doing with this device? One particular workload may work well on this device and another one may not on the same device, right? And you still might say it works, right? It's correct. So you need to look at that as well. So I think a combination of workloads and coverage model and then, just kind of seat of the pants.
Yeah, there is that experience factor, the seat of the pants piece of it, and that is important. There's also what's new in the design. If you're iterating a design, if it's the next generation, what's new, and certainly looking at those pieces of it are important. And actually, it's now 21 years since we first introduced the idea of formal written verification plans with the Veracity team, and people still don't actually write them down, or at least in enough detail. And even more than not writing them down, they don't actually do, Ashish, as you were saying, get the different teams together that are going to use the different methodologies and partition things out as to who's going to do what. So
I'd like to kind of maybe pop up a level and say, when I was useful as a technical person decades ago, my primary contribution was more as an architect. And at my current company, we're starting to do something that you don't get to do very often, to do a grounds-up new architecture from scratch. And as part of that effort, what I've tried to make clear to the architects, those whose job it is to conceive of how we're going to hook these pieces together, that part of their job is to specify an architecture that can be verified. And so it starts, from the very top of the conceptual design chain, that if you can specify, maybe not specify in the way that Formal thinks of it, but specify the architecture and document it, define it in such a way that it is, clean and has, nice edges. The problem as it flows through the whole sequence of design stages is more tractable. If you don't, you end up with a whole bunch of weird corner cases that people didn't think about.
Are you suggesting design for verification, Ty?
That's exactly what we call it. Yes. Actually, architecture for verification, but yes.
Architecture for verification is a great idea. Actually, RISC-V is a great example of open source architecture where so many clever people are developing these specifications in the RISC-V Foundation. And yet, with all of the combined intellect, people make mistakes. RISC-V weak memory model is a classic example. We only have 13 axioms, right? And yet it took a Princeton professor to find some inconsistencies. Now, RISC-V isn't the only processor specification that has had issues. The literature is full of memory consistency issues in all processor vendors, right? This is a hard problem. So somebody needs to take a step back, write it down. And actually, a lot of the challenges are in not knowing, right? That is where the challenges are. So,
okay, we have another audience question.
Yeah, I think on that whole theme, we talk about formal. There's also static verification. There's functional. I, as an engineer, am deeply skeptical of humans and doing their analysis because we all make mistakes. How do we figure out? How can we computationally figure out what is the highest risk for our coverage? And what is the best strategy to employ to do that verification?
So I'll give you a really quick one. I'm sure others would have their own view on this. So I would start by looking at what is the new additions, if it's a legacy design or it's a brand new one. If it's a brand new one, then I would look at highly optimized areas of the design to be my first targets for, by the way, I don't distinguish between formal and functional because I use formal for functional verification. I know the rest of the industry doesn't call it functional verification. They like to call it static or something else. But actually, never mind what precise technology you're still thinking of using, but identifying where your highest risks are, what is your timeline, when are you going to tape out, the team that you have at your disposal, their skill level, the tools, the compute infrastructure that you're going to throw your workload on, everything would count.
Well, everything counts, right?
Yes.
But even if you tried to distinguish legacy from new features, legacy bugs are still being found.
Absolutely.
Today, right?
So what do you mean by risk?
Well, I think when we look at our design, we as engineers, as architects, you inherently have an understanding of where there is more complexity in your design, more risk to be had, and we focus our validation on that. But let's just say Ty had a bad day.
Say that again?
Let's just say that Ty, as an architect, had a bad day and forgot something. That could have catastrophic effect down the line for the rest of the validation that we do. Is there a way for us to be able to objectively analyze and assess the complexity?
Yes, and for my design teams, we have a fairly specific, checklist or grading of features. The first thing we look at are non-programmable state machines. If you think of a CPU as a programmable state machine, so non-programmable state machines, and most importantly, non-programmable state machines that talk to other non-programmable state machines, because they tend to multiply in terms of error conditions, and particularly state machines that have multiple substates. So the key is to make sure that the architecture specification specified the control objects as state machines rather than just randomly coding RTL. Because everything's a state machine, you just can't really tell it is until you analyze it, right? So what I encourage the team is to start with, okay, what you're talking about is a state machine, just spec it as one, and name the states, do the transitions. And then we can see where there are places where this state machine talks to that state machine, which talks to that state machine, and then you end up with a memory system that has about 6 of them rolling at the same time, and you freak out.
Well, I was just going to address the issue of risk. So when you're talking about risk, I think you're talking ultimately about business risk, right? So are you going to be able to take this part and sell it to your customer? Is he going to be happy? So, you're talking about state machines, but perhaps for the particular way this customer is going to use it, or your customers in general are going to use it, one of those state machines only traverses 2 states. It never does anything else because that's just how it works out, right? So in which case, all that extra work to verify that thing, while it's good and it makes you more confident, it doesn't necessarily mitigate the risk of what it is of getting the part out the door and selling it to the customer. So I think you need to look at what the customer is going to do with the chip and how it's going to be used in the real world, and I think that's where you can start analyzing your risk from there.
So I'd actually like to get back to Ty's comment about design or architect for verification. It's a real interesting concept because I think actually in Silicon Valley, culturally, there has been a glorification of design and design creativity, and that's not necessarily aligned with architecting for verification. So maybe a little bit more emphasis on that architecting for verification would be
a little
well
humility
spent.
goes a long way.
Actually, Ty, what you mentioned is a great point, and we see this with customers where they are actually building full chips with CPUs, GPUs, and fabric, because the CPUs might have one memory consistency specification, the GPUs may have another one. Fabric would be driven by one of the bus protocols, and understanding what role would different components have on the overall structure of it is extremely important. I mean, you are a dream customer, Ty. I mean, if your architects are actually writing down specifications like that, I would love to get formal done on those things. I mean, this would be great.
it's a goal. It's still a goal.
Go ahead.
So one other people have been telling stories up here. I'd like to tell a story of a customer here, and the interesting thing this customer did, they started using Agile, and they had been using Agile for their software development. Then they started using Agile for their hardware development, and so what they were doing is bringing along the RTL and a virtual prototype and bringing along their software at the same time. What this had the effect of doing is that when they ran into a bug or an ambiguity in the spec, everybody was on the same page at the same time. You didn't have to have a hardware guy context switch and go back to 3 months ago when he was working on a specific peripheral, because now the peripheral implementation and the driver implementation, the virtual prototype that was going to test that, were all in sync, and that made the process a lot more efficient, and they actually saw those benefits.
That is the way
really
to solve
interesting.
Brian's problems that he was citing at the beginning of the panel, isn't it? You know, that agile flow where you bring together all of the key stakeholders, and
Well, there's at least one real-world case where it worked to bring these things along together.
It sounds like hell to me, but I can. Like, oh my God! Trying to negotiate with the software team in real time during design is. But I can see what you're saying. That might, I'll have to rethink that one.
Now, Mark, I want to go back to almost a throwaway comment that you made. That in response to an earlier question, you talked about workloads. Now, I presume that those workloads are because you don't just care about functionality anymore. You care about performance and power and other things that perhaps weren't the targets of verification in the past.
Well, yeah, certainly, all those things, right? So it needs not only to just work, it needs to work,
Well.
It needs to work well for whatever it is, for the use model, for the use case that the customers are going to use, or whatever application it's going to be used for. So yeah, you need to check it.
Do we have the
performance and
tools
power.
to find out if something is working and working well?
I think so, because we've been doing it, right? So we have actual silicon in the field that works. So I guess the answer is yes.
How do you approach that in the formal space too?
yeah, so actually formal is not considered to be the de facto technology for performance verification, and most of it is done with emulation and with software, which I totally agree with. But there are a lot of cases where you could apply this with formal, because a lot of the performance analysis is pretty much counter-based and making sure things remain within a certain bound or exceed a certain bound. Mm-hmm. Now, this is also a space where traditionally formal people have told the world that if you see counters, black box them and be very scared. But actually, there's nothing to be scared with counters, and you can actually do this, and I have done this myself. Again, we are doing a lot of exotic stuff, which is not the norm, so I know people might look at all of this with skepticism. But if you really were trying to establish a solid proof of whether those counters can exceed a certain bound, etc., then I would say at least take a look at some of the formal stuff. You still have to do what you still do with simulation and emulation.
So are we a victim of our own success here? And by that, looking at something like timing, for example. Right now, if we want to verify timing, we're going to use a big hardware emulator. Those are really nice, really successful, and the big three make a lot of money off of their hardware emulators. But actually, 30 years ago, when I got into EDA, what would happen is that a designer would design a specific block for a specific function, and he had a very strict timing budget for that block. And now you sort of look at the whole design and try and do timing through the whole design, and maybe you don't have the same design constraints. And again, architect for verification. Maybe this isn't for functional verification, but for extra functional properties.
That would be interesting. I don't know if we can do that. One of the biggest challenges I've had in my most recent team is that it was a ground-up development, so there was no software. There was no compiler when we were doing the hardware development. there was, barely a compiler by the time we got silicon down. So, we took our best shot. And now we're trying to use that learning to develop a second generation, in the ground up. But even so, there still won't be software for that thing, this new thing, in time, most likely to drive true performance analysis. And so, we're going to have to work with modeling, with high-level models, with System C type systems to try to get some feel for how the performance is coming along. And I don't see that changing that much unless you're doing the third iteration of System X, and you basically have some level of capability in the existing software ecosystem to drive a delta performance analysis kind of thing.
And talking about timing verification, we are in fact out of time, and so we will have to leave it there. Please join me in thanking our panelists today.